One of the aspects of biotechnology is having a lot of components available. And so this is where synthetic biology comes in, is that if you had a number of different promoters, for instance, that were well characterized and had standard connections, then those could be readily assembled in front of any gene. If you have ribosome binding sites of different strengths, those could be used. So there's where you get kind of the large numbers and the breadth, and of course, you're right, we want these to be reproducible. We want to be able to put them together in some fashion and always or be assured that there's some chance of them working when assembled. Promoter is a sequence of DNA where an RNA polymerase binds and starts transcription, the process that initiates expression of a gene. Ribosome binding site is a sequence, DNA sequence, in the RNA that binds a ribosome and initiates the translation of an RNA into a protein. So my laboratory has characterized a number of promoters that we use in bacteria to turn on the expression of multiple genes for metabolic pathways. If we want to produce a specific chemical inside a cell, we'll want to express many different genes that encode enzymes that catalyze those reactions. So we've characterized a number of promoters that allow us to differentially express the genes that encode those enzymes so we can try to balance the metabolic pathways. A metabolic pathway is a series of enzymes that catalyze metabolic reactions, chemical reactions inside the cell to transform one compound into another. So we, over the years, have either characterized or built some of our own promoter systems for controlling these metabolic pathways, but we never standardized them with cloning sites that would allow them to be easily compared. And we didn't always characterize all of these promoters. So a couple of years ago, I had a technician in the laboratory start to put BioBrick ends on all of the promoter systems we had. So maybe half a dozen different promoters, half a dozen different antibiotic resistance genes, origins of replication, and then assemble these and make them available for people in the laboratory to use. And in order for them to use them, she had to characterize the expression of a gene on each one of those constructs. It ended up being 96 different constructs. So this isn't groundbreaking work. But it's really basic and fundamental in that you have these series of components that you can assemble. They've got standardized ends on them that allow them to be assembled, and they're characterized. And I was amazed at the adoption of those vectors in the laboratory because, well, one, I had a high-quality person doing the work, but two, people could go on and look at the characteristics, and because the ends were standardized, they would always go together in the right way, and so they always got a result from using those. And I haven't had to force anyone to say, you got to use this vector for expressing your pathway. People just adopt them because they know now they're going to work. So when I talk about a BioBrick end, that's a restriction site in the DNA that when you cut it with a restriction enzyme leaves an overhang of some type, a series of unpaired bases in the DNA. And when that encounters its complement, then those unpaired ends can go together, and with DNA ligase, then you can stitch these together and make a full sequence, complete sequence.